Okay, good morning everybody, and thank you for joining us today. My name is John Barker. I'm a solution architect with Nvidia focused on deep learning applications in defense and national security. Today I'm going to talk to you about some recent advances in deep learning for defense and answer some of your questions.
Please stand by while your recording connection is established. This conference is being recorded.
Okay. Good morning. My name is John Barker. I'm a solution architect with Nvidia focused on deep learning applications for defense and national security. Today I'm going to talk to you about recent advances in deep learning for defense and answer some of your questions on that topic. If you want to type your questions into the chat box at the bottom left of your ReadyTalk screen, then they'll be being curated for me to answer either as I go along or in the Q&A section at the end. So I'm going to talk today mainly about specific advances over the last 12 months in deep learning, both applications and hardware and software that are applicable to the defense community. I will give a brief introduction at the beginning about what is deep learning, but this is really meant as a follow-on update webinar to the one I gave about a year ago on applications of deep learning to GeoIn. And at the end, there'll be 10 to 15 minutes of Q&A time. So, what is deep learning? The vast majority of modern AI, artificial intelligence applications, are based around machine perception. So that is getting machines to see, hear, and read what is contained within unstructured data like images, video, audio, and text. The traditional approach to these problems has been to have domain experts build feature extractors, things like edge detectors for images that they believe to be relevant to the task that you would like the machine to complete, and then have those feature extractors feed into typically linear classifiers that make a decision, such as in this case, is there a stapler present in the image? The problem with this approach is it's brittle. It's very hard to come up with feature extractors that are reliable for detecting staplers, but are not confused by other objects that may occur in images. It's also time-consuming and not very scalable because you typically have to build different feature extractors and train different classifiers or build different classifiers for different objects you might want to be able to detect. And then the pipelines for images are completely different for those for audio and those for text. So it's not really a scalable technology across different data types as well. So as a result, these approaches have failed somewhat to deliver human-level machine perception and have seen limited use in practice. Deep learning takes a different approach. It's a subset of machine learning, which is the process of training a model to perform some tasks, such as classification of what objects are present in images, by feeding that model many samples of labeled data for the task that you want to complete. So in this case, we have some sample images of 3 different types of vehicle, and then a sample image that doesn't contain a vehicle. And we wish to be able to have the network, after seeing many such examples labeled with the ground truth, learn to predict whether the image contains a vehicle or not for images it hasn't yet seen. The way that you train the model to do that is that every time it makes an error, you make some small adjustment to the model in a systematic way that will improve its performance against that error case the next time it sees the data. And then once the error on your labeled training data is small enough, you can fix the parameters of that model, this so-called deep neural network, which we'll talk more about in a moment. And then you can start to apply it to data that you haven't seen before, and hopefully it will be able to classify correctly whether there's one of these vehicles present or not. So what are these deep neural networks? They're very large versions of artificial neural networks. These are a mathematical construct that's been around for many decades, And it's a collection of very simple trainable mathematical units that collectively can learn complex functions. So when I say a unit, I might also say a node or a neuron. That's one of the green circles you see here. And then there are weights or edges that connect these neurons together. Typically, the neurons are arranged in layers, like you see here. You have an input layer where the data goes in, some hidden layers, and then an output layer. And the neurons in one layer feed forward information to the neurons in the next. Each neuron is actually just really a real valued number, and the weights, the edges that connect them, get multiplicatively applied, and then all of the neurons feeding from one layer feeding into a neuron in the next get summed together, the weight and a nonlinear functions applied. So it's actually very simple arithmetic that feeds forward information from the input to the output. But if you have sufficiently large numbers of these neurons and the weights are trained correctly for your data set, you can learn arbitrarily complex functions that map raw data to output decisions. So an example might be that we wish to train a network to perform face identification. So that is, given an image of a person's face, identify who it is. A network that you might train for this task would not have two hidden layers like I showed on the previous slide. It may have 10 or even 100 hidden layers. Each of those layers may have hundreds or thousands of neurons in them, and they could be and they're usually connected up in more complex local connectivity patterns, things that can capture local structure in the input images. Ultimately, a network for a task like this could have billions of trainable parameters, and you might train it on millions of images or even more depending on the task. But what's powerful about this approach is that for a task such as this facial identification, if the network is trained appropriately, the network will learn this hierarchical representation of features that are specific and relevant to that task of facial identification. So low-level features close to the data will be things like oriented edges and color gradients. Mid-level features will be parts of faces like eyes and noses. High-level features will be whole prototypical faces that are relevant to the task of identifying who the individual face is. But if we were to take exactly the same network architecture, apply exactly the same training algorithm, but we wanted to apply it to a data set of images of animals, we would find that the learned feature extractor and classifier are somewhat different and more appropriate for that task of identifying animals. So deep neural networks turn out to be a very robust way of doing machine perception because the feature extractors and the classifier are jointly learned to be optimal for the task you're asking it to perform, as defined by the data set that you train on. It's also a very generalizable technology. You can very easily take the same network, the same algorithm, apply it to different data sets, but not even just apply it to different imagery data sets, also apply it to essentially minor modifications of the algorithm to audio or to text. And it's an incredibly scalable technology because it doesn't rely on complex domain expert engineering to build the models, and in fact the performance of the models typically improves as you provide more training data. So just to emphasize that point, the input to a deep neural network is essentially a real valued tensor. So that's an n-dimensional real valued array. So almost any data type you can think of, including multi-source data types, can be represented as such a real valued tensor. And then at the output, it doesn't have to be a simple task like classifying whether there's a dog or cat in the image. You can also have much more complicated tasks like estimating a continuous quantity or clustering the images according to their visual content or audio content, or predicting the next item in a sequence. All of these tasks use the same training algorithm to train the deep neural network and just really minor modifications on the actual structure of the network. And so all this has led over the last 5 years or so to a point where for tasks such as visual perception of objects within an image, so that is taking an arbitrary image and labeling what object is present, the performance is now comparable to a human trying to label all the objects present in an arbitrary image. And we've seen a really rapid increase in the accuracy of these methods as the computer vision community has switched from these traditional handcrafted feature extractors through to deep learning-based approaches. But today I want to focus on applications beyond just image classification, and particularly those that are relevant to the defense community. Many of the examples I'm going to use were presented in April this year at Nvidia's annual GPU Technology Conference in San Jose, California. They are not all directly defense applications, but hopefully it will be clear how they are applicable in a defense context. So the first example I wanted to highlight came from Bingkai Zhang at BAE Systems, who at GTC showed similarly near human levels of accuracy on the task of vehicle detection in high-resolution drone imagery. He used hundreds of drone images to Apologies for the issue with the webinar. I believe it's now back up online. I'm going to wait 1 minute for any other people to rejoin and then resume. Okay, I'm going to resume. As I mentioned, Bingkai Zhang from BAE Systems trained a deep neural network in the same way I described before to detect vehicles in high-resolution drone imagery. He used hundreds of drone images and trained a deep neural network that was able to detect cars in parking lots with an accuracy of 99% and only 0.001% false positives. His team are currently developing this capability to support imagery analysts as a plugin in the Socket GXP environment, and that will be available later this year. Similarly, Digital Globe presented at GTC 2016 that they had also adopted deep learning for automatic labeling of vast quantities of the high-resolution satellite imagery they capture every day. They trained DNN's deep neural networks on both analyst and crowdsource labeled examples of objects of interest, as well as synthetic 3D models of those objects. And they were able to produce high-accuracy indexes of all the objects present in incoming images rapidly after they're collected. So this makes search for specific content or the application of geospatial analytics across that derived information in their cloud possible. And again, this removes the time-consuming work of manually labeling images by the analyst and frees them up to focus on the mission-focused analysis on the extracted information. At this point, I'm just going to insert an advertisement, actually, that Digital Globe will be, in partnership with Cosmic Works and Nvidia, launching a satellite imagery object detection challenge in the coming weeks. The challenge will provide satellite imagery data and an interesting object detection challenge for the participants. You can register today at the URL shown on the chart, and it's expected to launch within 2 to 3 weeks, and deep learning could be an excellent technology to apply to such a challenge. The application of deep learning to remote sensing is not limited to object detection, though, in the way that we've shown in the previous two examples. It can also be used for discovery. TerraPattern recently launched a web service that uses a deep neural network to automatically index at a fine granularity all the locations in a large collection of satellite imagery. This enables you to then do visual similarity-based search across that collection of imagery, and it can be carried out almost instantly. So this allows an analyst to ask a question like, find me all other locations that look like this example. So in the example we see on the chart here, TerraPattern is automatically finding all the baseball diamonds in this wide area image based on the prototype example on the top left of the search results. Recently within Nvidia, we have been exploring how to leverage some of the advances that have been made in the autonomous driving space for high accuracy object detection in remote sensing images. So what I mean by that is a new deep learning approach that's being largely leveraged in that autonomous vehicle space is able to simultaneously detect all objects of interest in an image and draw high accuracy bounding boxes around them. And it does this by having a network that's trained to simultaneously optimize both of those tasks. So instead of training the network on small image patches with vehicles in them, you train on whole large images with the bounding boxes already identified as your training data set, so a much richer training set, and your output for your deep neural network is for every location in the image, essentially a confidence of which vehicle is there and a bounding box relative to the vehicle. The reason that you would want to do this is that you get an unprecedented accuracy in both terms of detection of the vehicles and the quality of the bounding boxes, and you get it in a very computationally efficient one-shot network. So, for example, the images that are shown on this chart in their raw format are actually on the order of 3,000 by 2,000 pixels, and we can detect all of the vehicles present in one of these images and draw these high-quality bounding boxes in tens of milliseconds, whereas it would take much longer with a patch-based object detector applied in some kind of sliding window fashion. To give an example of the performance of this type of capability, I'd encourage you to watch our CEO Jensen Huang's speech at GTC 2016, keynote speech at GTC 2016, and also his speech at CES 2016, where he showed that same technique being applied to ground-based video in an autonomous driving scenario, and it was able to detect pedestrians, vehicles, and road signs, even when they're partially occluding each other, and draw bounding boxes which could take that occlusion into account and show the whole extent of the occluded object. And a minor modification of that approach is also able to label actually every individual pixel in the scene by type, as you see in the example on the right here. And Jensen showed that this type of network can be run at hundreds of frames per second on an embedded GPU system with this kind of detection accuracy. And so I believe that in a defense scenario where we wish to perform object detection in images, this is going to become the prevalent way that task is carried out. Again, at GTC, a researcher from Princeton University presented his results on extending deep learning-based object detection to 3D volumetric data. In this case, the data was captured in interior scenes using an RGB camera coupled with a non-visible spectrum depth sensor. Together, those two could be turned into a 3D volumetric representation. And then a natural extension of the 2D image case for deep neural networks to 3 dimensions can be built, all using the same underlying deep learning software and trained to produce 3D object proposals. These can then be subsequently filtered and refined to give 3D object detections with bounding boxes. The same method could obviously apply to larger scale 3D data, such as LiDAR point clouds or point clouds derived from structure from motion information. Deep learning is not just applicable to imagery data, though. I suggested this earlier. Here is an example of where the same, actually very closely related image processing techniques are used to process spectrogram data. So in this case, one of our partners, Intelligent Voice in the UK, showed at GTC that they were able to take input data that was recorded audio utterances in one of 20 dialects from 7 different languages. They could convert that into a spectrogram representation, so a time frequency representation of the audio, and then pass that into a deep neural network that was actually originally designed for image processing, but is now being applied to the spectrogram data. And the output of their network was a classification of what dialect was being spoken. Their preliminary results show that in the case of classifying the specific language, they achieved an accuracy of nearly 84%. And in the case where they had 5 guesses at the language and the correct one needed to be in that 5 guess, they achieved nearly 99% accuracy. And this is all achieved without needing any new deep learning training or testing code. They actually use the Nvidia Digits deep learning training tool, which we will talk about later on. Baidu, the Chinese internet search giant, receives a huge amount of its search queries as speech queries through mobile platforms. So these queries come in both English and Mandarin. Baidu's developed a deep learning-based speech recognition system using the cutting-edge technology of recurrent neural networks. It's beyond the scope of this talk to go into the details of recurrent neural networks, but essentially what they are is an extension of the deep neural network architecture to allow the model to learn sequential patterns in sequential data. So it can do things like classify whether a particular pattern has occurred in a sequence or predict what words might come next in a sequence. And this is important for improving transcription accuracy. If you want to try and transcribe what word is currently being spoken, it's very helpful to have an understanding of the words that have previously been spoken and a prediction of what words will come next. This system actually now has an error rate that is more accurate than human transcribers in both of these languages, that audio captured in noisy real-world environments. And again, this can be built with the same deep learning software as can be applied in all of the other examples I've described. Researchers at the Children's Hospital of Los Angeles gave a nice example of GTC, showing that deep learning can also be applied for prediction tasks in a multimodal streaming data context. So they created timeline visualizations of all the incoming data relevant to a patient. So for example, the lab results as they came in over time, the patient's vital signs, the drugs that had been administered. And they converted these into this timeline representation you see on the left, where the grayscale of the pixel essentially denotes some property of that data stream, or the value of that individual data stream, and they are all concatenated vertically into this one big timeline representation. And then they trained an image recognition deep neural network to predict the probability of survival for patients based on these timelines. Their system achieved an impressive performance on test data, which was not used in training, obviously, with an area under the ROC curve of 90.3%. And they're currently transitioning to recurrent neural networks too, similar to what I described in the Baidu speech example, so that they can improve the exploitation of the rich sequential information in this multimodal data. The final example I'm going to talk about, application example I'm going to talk about, was presented at GTC by the Universitat Autónoma de Barcelona. And in many defense missions, there is limited or no data for a specific scenario, and this is often a reason cited that machine learning or deep learning may not be applicable to that problem. Because it's true that deep learning methods typically rely on large amounts of training data. What was shown in this GTC talk was that you could use a video game development environment called Unity to produce simulated vehicle-mounted camera and depth data for complex 3D worlds. So you can think of a modern 3D video game. They essentially drove a car around that world, capturing the data that you would get from vehicle-mounted cameras and depth sensors like LiDAR. They then, instead of training a model wholly on this data, they mixed it in with publicly available real-world data sets. And their task that they were trying to perform was this so-called semantic segmentation task, which is labeling every pixel in one of the camera images by type, so trees, pedestrians, road, etc. And what they found was that they improved the segmentation accuracy across most of the object classes when compared to real-world data alone. So this has the benefit of bootstrapping that real-world data set with a much, much larger volume of simulated data that overall improves your model performance when you then deploy back into the real world. And it also has the benefit of allowing them to simulate environmental conditions and scenarios which they may never encounter in the real world. So, for example, overlaying snow over the scene or some other weather condition. There are far too many advances in deep learning applications relevant to fence over the past couple of years for me to cover them all in this talk. I've picked some of the ones that are most interesting to me and I think have broadest applicability, but some of the other diverse application areas where we've seen activity and impressive results are listed on the charts here. If you think that deep learning might have relevance to your particular application, we'd be happy to discuss that possibility and help you get started with developing your deep learning application. We'll have contact information given at the end of the talk. Also, feel free in the questions Q&A session to ask about any of those applications listed if they're of interest. So now I'm going to talk about advances in deep learning hardware that are relevant to accelerating the type of applications we've just talked about. So as I've already described, the combination of these deep neural networks trained on massive volumes of data has led to amazing results in machine perception. However, training deep neural networks with billions of parameters on millions of images is incredibly computationally expensive. So the third key enabler to achieving these recent results has been the use of the GPU for accelerated computing. So I want to give a brief but not too deep explanation of why that is so. So when training deep neural networks, the vast majority of the computation is actually concentrated in two functions that are repeated many times. I described that you feed forward the information from one layer in a neural network to the next through this multiplicatively weighted sum of the values of the neurons in one layer feeding into the next. It actually turns out that to implement that in practice, it can be implemented as one big dense matrix times vector multiplication, or in fact, in practice, you normally perform it as a matrix-matrix multiplication. The second key operation is that in the computer vision cases, we have both, we need to perform this operation called convolution. So that is essentially that you have these small little patches of features, something like the oriented edges that I showed in the face recognition example, that you're going to need to slide each one of over a collection of input images. Both of these operations, dense matrix vector multiplications and convolutions, Nvidia has been using GPUs to accelerate for many years by exploiting the inherent parallelism in these operations. So dense matrix vector multiplications commonly occur in applications like high-performance computing applications like simulations. Convolutions have also been used extensively in computer graphics for things like post-processing effects on produced graphics. But furthermore, beyond just accelerating those individual operations, there's a huge amount of parallelism that can generally be exploited in the training of a deep neural network. Some examples would be you can parallelize across the input images, or you can parallelize across the pixels within those images, and repeat operations like that over the subsequent layers of the network. So the message is that deep neural network training is an embarrassingly parallel problem. GPUs are a great fit for this kind of problem. The computational requirements are a great fit because GPUs excel at massive parallel computation and matrix operations. And furthermore, the big data being used to train deep neural networks also means that high memory bandwidth is required for rapid transfer of the data from system memory to the processors. And this is also an area where GPUs excel. So overall, this means that GPU acceleration can enable these cutting-edge AI application results in practical training times that would not be achievable otherwise, and in a smaller physical footprint and lower power envelope than alternative computational systems. To give a concrete example of what kind of acceleration you can see, I'm going to talk about the Tesla M40 server-based GPU accelerator. This is the fastest currently available accelerator for deep learning in the PCI form factor. And the benchmark result that we're showing on this chart is for a network called AlexNet, which was one of the first proposed human-level performance networks for classifying the objects in imagery. And we're training it in a deep neural network framework called CAFE, which we'll mention again later. And we find that on a single GPU server with 4 Tesla M40s, we can reduce the training time for that CAFE, for that AlexNet network from 13 days down to just 1 day. And the reason for this is precisely because we are using the 3072 CUDA cores in this accelerator to accelerate the parallel processing that I described in deep neural network training process. But the scale of networks that people wish to train is continuing to grow. More recent networks may feature not the 7 layers that we see in this AlexNet network, but hundreds of layers in a network like Microsoft's ResNet network. And also, the demand for more rapid training never goes away. Reducing from 13 days to 1 day is a fantastic result, but we would like to continue to reduce further, because the data scientist still wants to be able to iterate fast on the model training process so that they can tune their hyperparameters or train multiple variants of their network. So as such, Nvidia continues to innovate to provide faster GPU acceleration for deep neural network training. And at GTC this year, Jensen Huang, our CEO, introduced the Nvidia DGX-1, which is the world's first deep learning supercomputer. So this is a 170 teraflops half precision server containing 8 of our next generation Tesla Pascal architecture P100 GPUs. And they are linked together by a new interconnect called NVLink, which allows much faster GPU to GPU communications, which is critical as we wish to scale up to deep neural networks that are too large to fit in the memory of a single GPU. And we want to see strong scaling of the training of that network. So as we add more GPUs, we get a linear increase in a reduction in training time. To put into perspective the power of this DGX-1 system, we actually trained that same network I described, but in a distributed training process. So the same AlexNet network trained across the 8 GPUs in the DGX-1 simultaneously. And we found that we could train that network now, instead of in the 1 day on a 4 Tesla M40 server, in 2 hours. To train on dual Xeon CPU servers, it would take about 150 hours, and it would require about 250 nodes. And there's actually a slight caveat on that, which is that we're assuming that you would get the same linear strong scaling across the CPU nodes, which is unlikely to be true. The heart of this DGX-1 supercomputer that provides this impressive performance is, as I mentioned, the Pascal architecture Tesla P100 GPU. As of yesterday, we announced that this GPU is actually available in 2 form factors. The form factor, as we see above, that is only available and used within the DGX-1 platform, but also a PCIe-based variant, which comes in both 16 gigabyte and 12 gigabyte configurations. So what does all this mean in terms of the acceleration of training that AlexNet network we talked about over the last few years. I mentioned that there's a continuous thirst by the data scientists and researchers to reduce the training time for these networks. Over the last 3 years, we have seen a over 60 times improvement in the reduction in the training speed for that AlexNet network as we go from the Kepler architecture K40 GPU in 2013 through to the 8 times P100 NVLink enabled in a DGX1 platform in 2016. It's not just the improvements in hardware that have enabled this. It's also the accompanying software, which we'll talk more about in a moment. When we compare the Tesla K40, we were utilizing earlier versions of the CUDA implementations of the deep neural network software, and so some of the improvement has come through those software improvements as well. Before we move on to software, I also wanted to point out, though, that many times you wouldn't necessarily want to deploy your trained deep neural network on a server such as the DGX1. It may be that your target application is an autonomous vehicle. So you need the DGX1 to be able to train on hundreds of millions of images and tune billions of parameters. But you want to take that trained network and actually deploy it within a vehicle or on board a drone or on board an aircraft. So late last year, we introduced an embedded GPU called the Jetson TX1, which is a Maxwell architecture GPU, so the same architecture as was in the Tesla M40 I described, but with 256 cores instead of the 3072 there, but actually using much less power and can perform deep learning inference, so that is applying a trained network to new test images in using under 10 watts of power. The fantastic thing about developing on one of the server-based or workstation-based GPUs and then deploying to the embedded environment is that because the architectures are common across all those devices, you can take the same software, the same CUDA code, and compile and run on any of the devices. So to take a trained deep neural network that you've trained in your data center on a Tesla server, Tesla GPU in a server, and deploy onto a Jetson TX1 is essentially a task of copying over the trained network and software, and you can run it without modification. So the message is that all of the GPU systems which we've introduced over the past year and before are one architecture for end-to-end AI, from training through to testing through to deployment. So now I'm going to talk about the accompanying advances in deep learning software that we've seen recently. So this chart, I'm sorry, is a little bit complex at first. I'll take the time to walk through it. At the top, we've split out the 3 predominant deep learning applications. So computer vision, which we talked a lot about, speech and audio, which we talked a little bit about, and then also natural language processing. So things like named entity recognition, document classification, sentiment analysis. Today, all of the deep learning applications in those areas are built on top of one of the deep learning frameworks that we see in the middle. So Caffe, we mentioned earlier, is a great deep learning framework for computer vision applications, but there are many other frameworks, and these are essentially domain-specific programming languages that lend themselves very well to deep learning applications. Some are more applicable to a production high-performance environment. Some are more applicable to particular data types like images. Some are more useful in a research environment where you want to see a much clearer representation of the mathematics translated into code. They all offer somewhat comparable functionality in terms of being able to manage your data sets, train a deep neural network, and then test it against new data. All of these frameworks are accelerated by the Nvidia Deep Learning SDK. So this SDK are highly optimized CUDA libraries and associated applications that provide the building block functions that these deep learning frameworks require for achieving GPU acceleration of deep neural network training. So what I mean by that is, if you use, for example, the Theano deep learning framework, you'll typically be coding your deep learning training process in Python, but Theano will be accessing a highly optimized CUDA-C implementation of the functions that you're calling through Python. And that implementation will in turn be making calls to libraries such as Nvidia's cuDNN library, which provides GPU-accelerated, highly optimized implementations of the convolution function that we talked about earlier as being applicable in computer vision. As well as cuDNN, we have the cuBLAST library, which existed before deep learning for accelerating linear algebra operations, cuSparse, which accelerates sparse matrix operations, the Nickel library, which is a collection, GPU-accelerated collectives for GPU to GPU communication, which become very important, again, as we try to train deep neural networks across multiple GPUs within a single server. And the GPU inference engine, which we recently announced that I will describe in a moment, for producing optimized runtime implementations of a trained neural network. So what is cuDNN? cuDNN is a key contributor to this speed up in AlexNet training performance that I talked about before, this over 60x speed up for P100 and cuDNN versus K40. It's high performance GPU accelerated implementations of the building blocks for the deep learning frameworks. So that is the convolution operation I mentioned before, but also some of the other layer types that occur in modern deep neural networks, so things like the fully connected layers, the spatial pooling layers, and importantly for the recurrent neural networks, the ones that have sequential memory applicable in speech and natural language processing, we recently added support for long short-term memory cells. Again, it's beyond the scope of this talk to go into the detail of what those LSTM cells are, but essentially they are one of the leading methods being used in recurrent neural networks in those applications. And we introduced optimized implementations of those cells that offer a significant speed up over the implementations that were already existing in the deep learning frameworks. And obviously all of these, the implementations of these functions are tuned for high performance on NVIDIA GPUs. Another view of the NVIDIA deep learning software platform is that on top of the deep learning frameworks, we also provide a software system called Digits, which I'll talk about in a moment. Digits is a graphical interface for managing training data, training deep neural networks, assessing the quality of those networks, and then extracting the trained network. And then we are now providing the GPU inference engine, which is aimed at deploying that trained network from Digits into an environment, whether it be a data center running a web service or an automotive environment or an embedded robotics application. So Digits is an interactive deep learning GPU training system. So that means it allows you to easily import data sets. Predominantly that's imagery data sets, but you can import other data types somewhat more manually, but you can schedule, monitor, and manage neural network training jobs against those imported data sets without ever writing a line of code. The intelligent voice dialect classification example I described earlier did exactly that. They imported their spectrograms of speech into Digits as images, trained a deep neural network, and tested it without writing any new code. It allows you to analyze the accuracy and loss function of your network in real time, and it can scale training jobs across multiple GPUs automatically. And the new approach I described earlier to object detection in aerial imagery, or in any imagery in that fact, where we simultaneously train the network to detect and draw bounding boxes around all the objects in a large image, we've recently added in digits 4 as a capability that you can train, again, without any additional coding, just given your data set and your network architecture. And once you've trained your network and you want to deploy it in a high-performance inference environment, so as I mentioned, in a data center on something like the low-powered Tesla M4 GPU running a web service, or in an automotive environment on something like the Drive PX, the GPU inference engine will take that trained network out of digits and the network definition, and it will produce an optimized runtime. It will make optimizations such as fusing together subsequent layers of the trained deep neural network that can all be carried out on the GPU in one efficient computation, rather than running each layer of the network independently, feeding one into the other. And the upshot of these many optimizations that the GPU inference engine will make is that you get a much higher inference performance per watt over both a GPU implementation without the GPU inference engine and over a CPU implementation. And on the right, we see some examples for the Google network, which is a more complex network than the AlexNet one that we discussed before, but it's actually the network that was used in the intelligent voice dialect classification example. And we see that we can achieve up to 16 times more inference performance per watt using the GPU inference engine. So at that point, I'm going to finish and try and answer some of the questions that we've had coming through. I wanted to point you towards 2 things before I do that. The first was, if you wish to get started with deep learning on your own, you can go to developer.nvidia.com/deeplearning, and there you can find links to more training material that gets much more in-depth on the technical details of training deep neural networks and GPU acceleration. And you can also find links to download all of the deep learning software I've talked about, so the deep learning frameworks, digits, cuDNN. And the other thing is that there is an email at the bottom right of this slide, geoint@nvidia.com, where you can send any follow-up questions that you maybe don't want to post in the chat box here. And so at that point, I'm going to spend 10 minutes trying to answer some of the questions. So one question is, in the object detection example, does the neural network still work on patches? And if so, how are the patches presented to the network? So is the scene chopped up into 256 by 256 patches that are shifted a pixel at a time, the same as the pedestrian example? So the answer is yes, you can still apply the network to a smaller image, and that's really the power of the approach. If we have a network trained on patch-based images, it's computationally very expensive to apply that in a kind of sliding window fashion over a large image, whereas this end-to-end trained network can be applied very efficiently to the whole larger image to produce the object detections of bound boxes, but it can actually still be applied to a much smaller image as well. The caveat to that is that the objects that you're trying to detect need to be present at the same scales in your training data as the data you're going to deploy the network against. So what I mean by that is, if you, in your input training data, your vehicles that you were trying to detect are 10 by 10 pixels, if you then take a patch-based training data where the vehicle fills up the whole image and is hundreds of pixels, the network won't detect it. So this is the same with essentially all computer vision-based deep learning systems, where the type of variance that you're going to see present in your test data needs to be represented in your training data set. So another question was, so a question about scaling. How many GPUs are needed for a 4-layer deep neural network? it depends on how many neurons are in each of those layers, how the layers are connected together, and how much data you're trying to train the network on. So there isn't really a definitive answer. I guess what I would say is that a 4-layer deep neural network is very small by today's standards, although in the recurrent neural network example, where you're trying to learn sequential patterns in data, for a 4-layer network might not be uncommon. However, there's additional computation required in those kind of networks. So again, you could easily scale over a single GPU. I guess what I would like to emphasize, though, is you can train many cutting-edge, high-performance deep learning applications, something like the vehicle detection in aerial imagery I showed, on a single GPU. I have trained that network that I showed in the images using a single Titan X GPU with 12 gigabytes GPU memory. The question about how do you do semantic segmentation. So I didn't really go into any of the details about convolutional neural networks specifically or how they're structured, but essentially the way they are typically structured is that they kind of have this triangular-like structure in the size of the layers. So as you input an image, the size of the layers that it propagates through gets smaller until the final output decision. In the case of semantic segmentation, what you actually do is, in the latter part of the network, you re-expand the size of the layers up until you have a layer whose size and dimensions match the input images. And essentially, then you train the network to directly predict all of the classifications for the individual pixels within that output layer. And your objective function for the network is to compare those predicted pixel values to your ground truth segmented image label. And so this is something that a lot of the neural network frameworks will allow you to do now. It does require some particular layer types for that re-expansion process, if you like, that decoding process that back up to the size of the input image. But many of the deep learning frameworks will allow you to do that today. So there's a question about, in the aerial imagery example, whether I was talking about object tracking or object detection. And it's similar to face recognition technology, where there's a difference between detecting an object and uniquely identifying it. So, and is this a concept in deep learning? So the short answer is yes. In the same way that in facial recognition, you could train a deep neural network to perform both the detection of a face, but also the identification of a particular face, or also the a prediction of the age or gender of the face shown. You can train a deep neural network that would attempt to identify specific individual vehicles. Having said that, that is a much more difficult task than facial identification. Typically in data like I showed, vehicles are very small, many of them look very similar, and I would argue that there's going to be plenty of cases of particular vehicles that you would simply never be able to get reliable differentiation from other vehicles just using color imagery in that way. Okay, so there was a question about how did the spectrogram analysis work with the neural network, which was trained for image processing without training on spectrogram data. So my apologies if I wasn't clear on my explanation of that. The network was trained on spectrogram data. The spectrograms themselves were treated as if they were images. When I said that the network was a neural network designed for image processing, all I meant by that was that the structure of the neural network was one that was proposed for image classification, and it had properties which turn out to be useful for classifying spectrograms when you treat them as images. So things like sensitivity, that it could deal with translation of features within the image. So if there was a particular spectral feature that was important for classifying a particular word, transcribing a particular word, or in this case, sorry, classifying the dialect, it doesn't matter where that appears in the spectrogram, the network could find it and make use of that information. So yeah, the network architecture, the number of layers, the number of neurons in the layers, and the connectivity was one that was proposed for image classification, but the network was entirely trained on the spectrogram data. Okay. So a great question here. Why is Ubuntu the operating system of choice here? We see that on the DGX-1 appliance as well, getting deep learning into HPC needs Red Hat, CentOS, etc. I'm not going to answer why Ubuntu is the most popular choice. It would be a question better aimed at the deep learning framework developers. But what I will say is that although the DGX-1 also runs Ubuntu, we have also released over the past year something called Nvidia Docker, which is an extension of the Docker containerization framework, which will allow you to deploy containers running Ubuntu with GPUs passed through into them from other host operating systems. In the case of the DGX-1, you would still be running on Ubuntu, and you would be probably creating a container running Ubuntu to run your deep learning framework. But in those other OS Linux operating system environments, NVIDIA Docker might be a great solution to deploy deep learning into an HPC environment that needs a different underlying Linux distribution. Okay. So when training a deep learning network, is it better to train with all the data at once versus fine-tuning a pre-trained network with new data? My concern is that a pre-trained network will resist weight modification in the new data source because it's settled into a local minimum. This is a great question. So typically, best practice these days is to start with a pre-trained network and fine-tune for your data. But you have a choice to avoid some of the issues that you're worried about, that perhaps the data is overly fit to the data it was pre-trained on. You actually have a choice as to how you fine-tune the network. You don't necessarily have to fine-tune the entire network end-to-end. You may find that the lower layers of the network, closer to the input data, don't need to be, can remain essentially fixed from the pre-trained network. So those low-oriented edges and color gradients may apply equally as well in some other image classification setting. But the higher layers of the network, closer to the actual classifier, do need fine-tuning more or even retraining from scratch. So most of the deep learning frameworks, for example in digits, will allow you to identify which layers you want to remain fixed, which layers you want to train, and whether you want to initialize the layers randomly or initialize them from the pre-trained model individually. Okay, I'm going to answer one more question as we're basically out of time. Okay, there's a question here about what about if I have lots of data but it's unlabeled? How do I get started in this case? In that case, the fine-tuning, the pre-trained network I described before could be your friend. So it actually turns out that in a lot of cases, if you have you've trained a network for image classification in one setting, say on dogs versus cats, much of the network's ability to just recognize visually similar and visually dissimilar images will actually transfer over when you apply the network to other data, other image that doesn't contain dogs or cats at all. So what I mean by that is, if you take that pre-trained network for dogs and cats and you apply it to images of commercial aircraft and military aircraft, the network won't be able to classify those images as commercial aircraft or imagery aircraft, but some of the higher feature layers will be different in the two cases, which means that you can extract those higher feature layers for the aircraft, commercial aircraft and military aircraft, and use them as feature vector representations of those images where visual similarity will be preserved under a metric like Euclidean distance between the vectors. So then you can cluster those unlabeled images according to visual similarity. Then the other thing that you can do in the case where you don't have much labeled data is that you can actually adopt what's called unsupervised learning. So that is, instead of training your network on an objective function that is predict the animal present in the image and your loss function is how well you can perform that task, you instead train with an objective like compress my image, then uncompress it accurately, and you train the network to perform that task. Then the feature layers at the middle of that network, where the network has compressed the image, so that is, it has less parameters to describe the image than are in the input image, those can be used for tasks such as clustering based on visual similarity. So those are the two approaches you can take. So at that point, I am going to say thank you again for attending, and please reach out to us on email if you'd like to